Hello, right, so again, you haven't checked me here. Right, where was I? I'm blinking again, so I do that. You'll notice that it's like a motif, isn't it? Steve starts filming, points the camera, starts blinking. Past point 14, I can't even remember what the criteria says. Do not worry about it, okay? It's all about design solutions for basically when you go through the sound barrier. So we've said before that when we go through the sound barrier, okay, we're going to have two problems with transonic flight. Okay, now the video on Mach numbers and things, and defining Mach and defining critical Mach, which is for merit point 5, okay, which is the easy bit. It's one of the easiest merits that we do. That tells you all about the sound barrier and how you break through it, right? So P13 is actually harder than M5 in my view. What we talked about with P13 was we talked about the centre pressure moving, but the key concept that we discussed was that inside a shockwave, in that shockwave flow, right, where you have not got laminar flow in that shockwave, what you have got is an absence of lift. There's no lift in that under a shockwave. That causes problems with control. Right, so you get basically P14 is what design solutions do you get for do you use for loss of control effectiveness in the transonic range? What does that loss of control effectiveness mean? Right, well, before we go to the Spitfire, we'll go to the red one here. Okay, and we'll just it happens in roll and yaw, but we'll stick with pitch for now. So this horizontal stabilizer, okay, is an upside down aerofoil, so therefore our shockwave is going to be on the bottom of it. Right, the curviest bit of this is this. There's going to be a shockwave there. Now, if that shockwave moves along, you've only got tiny little elevators on here, and this is what the Bell X1 found out with the Americans. If you look at the PowerPoint I put on about the history of breaking the sound barrier, the Americans found that when the Bell X1 travelled near, they had the idea to put the tail high up. Now, the reason for that, going back to Spitfires, I'll go back to that in a minute. But the main problem was that the shockwave, if the shockwave moved back over the tail, and when the shockwave, you remember this control surfaces from assignment 2, this uses lift to control. It's all about lift. Sorry, no, assignment 3. Sorry, not assignment 2. Assignment 3, we talked about how flying control surfaces work, and they modify lift. If there's no lift there, if there's no laminar flow over the control surface, they won't work. So you're in the cockpit and you're doing that. If you haven't got laminar flow, you can do that as much as you want. The aircraft is not going to change direction. Right, which brings me to submarine Spitfires and Hawker Tempests and Typhoons, the original Typhoon, diving headlong after things called V1 flying bombs. Now the V1 was a jet-powered flying bomb. Basically the very, very first cruise missile, and it was launched by Hitler against the UK in the late the late part of the war, 1944 onwards, 1943 I think, as early as that. And the slang term for them, they were called doodle bugs or buzz bombs, because they made like this, and when you stopped hearing the zzz, it just goes, and it went silent. People used to worry because that was when it was in its final descent phase into the town. And basically, launching them from Germany and Holland and places like in occupied Europe, they could hit London. They couldn't hit anywhere, they couldn't specify which part of London they hit, but they could hit roughly the Greater London area. And they just launched them blindly. They had a gyro to keep them on a straight and level path, and then they had like a timer, and then they set that to say, okay, at this certain level, they cut the fuel to the engines, it would glide down into a glide, and it would explode when it hit the ground. A terrifying weapon. So there's the V1. The V2 was the bigger rocket one, which was the first the first kind of ballistic missile. It wasn't intercontinental, but it used to fire up in the air and come down like that. The V1 would glide with wings, and then run out of fuel and drop down onto a city. The V2 would be fired up into the air, really, really high into the stratosphere, and then it would come down on a ballistic trajectory. None of that has got anything to do with, well, has a little bit. So, in order to shoot down the V1s, the Spitfires used to chase them, and this is where this first started to come across the sound barrier. And what they found was two effects used to happen. One would be you get the separated floor at the back of the wing. Now this separated floor actually, spoiling a little roundel there, but would form like an area like this at the back of the wing, and it would get bigger. And sometimes if the tail was low or at certain angles of attack, then what you'd find is this separated floor here, right? With an aircraft with a low down tail, that all of this would be non-laminar flow. This would all be turbulent flow, and the tail would get stuck in turbulent flow. Okay, that meant the elevator wouldn't work. So if you were in a dive and you thought, oh, I'm going a bit quick here, right? And some Spitfires achieved speeds over 500 miles an hour in a dive, yeah. They'd be like that. All of a sudden they get this buffeting, which was caused. The buffeting was caused by the turbulent air striking the tail and making the. Imagine all that turbulent air making the tail do this and waggling it about, and it's on the end of a big stick, the fuselage, so you're waggling it up and down. Imagine that's your head in the cockpit and you're getting this. Yeah, your head's like that all the time. So they got buffeting, and they got mainly loss of control effectiveness. They went to pull out of the dive and nothing happened. Yeah. The only way to pull out that dive was to reduce the engine power, slow down, so this got smaller. Yeah, so that then stopped hitting the tail, and this separated flow got smaller and smaller and started to get littler, and then you got your control back. And some people died. Some Spitfire pilots, their colleagues, their wingmen were watching them, and they were coming in to watching them try to shoot down the V1s, try to chase the V1s down, and you know, they were saying pull up, and they're like, I'm trying. And then the other thing that happened was the canopies at that speed, the canopies were only designed to be opened and closed at about 300 miles an hour, 300 knots or 200 knots. At over 500 knots, the air pressure on the canopy, because the canopy used to slide back like that on a rail, right, the air pressure was forcing the canopy onto the aircraft and forcing it onto the metal rails. So you imagine if you had like two metal rails sliding against each other, yeah, and I stood on that metal rail, you wouldn't be able to slide it, would you? Yeah, so you found that you couldn't even bail out of the Spitfire. So I've actually got a model Spitfire here. You can see that closer up. You can see the canopy that slides back there. So it's in a death dive. It's got separated flow off the wing, hitting the tail. It's also got, now the Spitfire, I don't know if you can see on that bit there, has quite a large elevator. Okay, with trim tabs. It's got quite a large elevator. Now, the other thing that happened was the shockwave. They didn't really know what shockwave, well, they knew what shockwaves were, the scientists did, but the pilots didn't really understand that much. And the shockwave would start there and get bigger, and when the shockwave moved back close to about Mach 0.9, yeah, it would come back to about there. And if you think of that as the elevator, the shockwave is covering the elevator. There's the elevator there, there's the elevator joint. So almost the whole elevator is in a shockwave. So it's not got laminar flow. Right, two options for this. So now we're going to develop something else. We're going to develop another aircraft. So I'll draw you a Hawker Hunter. I'm not as good at drawing them as I am Spitfires. It's a bit like that, and it's got a kind of rounded nose like that. It's got a fuselage, that sort of shape. Okay, and we're going to put one wing there, and the intakes for the Hawker Hunter at the front there. So here's my Hawker Hunter. So we need to alleviate this problem. How we're going to fix it? Dead simple. Right, the first thing they did was they said, right, okay, what we're going to do is we're going to make sure we're going to put the tails higher up. Okay, so the tail is higher, so that gets rid of this problem here, doesn't it? So it's out of that cone, it's now missing that. Jobs are good. That worked okay, yeah, until you got to the point where you went to go a little bit faster than actually just the speed of sound in Mach 1, sort of Mach 1.2 and things like that, and then you start getting these shock waves here. Yeah, okay, and the shock waves covering that. Now, yeah, you've solved one problem, but you haven't solved the other problem. So what they then did was, says, right, what we'll do is we'll develop something so we have a thing called an all-flying tail. So instead of having a separate elevator, so I'll just draw that in plan form there. So that's what this tail would look like. It would have like a, and you can still have your little balance horns there. That was your elevator, and that is your horizontal stabilizer. Okay, so this is, we'll make it all one piece, right? And we'll make a pivot in the middle, and you've already done this. Okay, so it's pivoted about there, just ahead of the centre line. That's where it pivots up and down. So when it's up it looks like that, when it's down it looks like that, right? And that is either a tailor one if it moved backwards and forwards. The first ones were just stabilators, they all moved up and down together, okay, so they just controlled pitch, and they called them stabilators or all flying tails or all moving tails. The advantage of that is now the joint's not there, the whole thing moves up and down, right? So when the shock wave is covering any point, so you've got lift all over it, yeah, so there's your lift there, right? This has got lift all over it, that's got lift all over it, but only this part of lift is used for control, okay? So now put your shock wave anywhere you want, you put shock wave there, you can put shock wave there, you put shock wave there. It's going to, sorry, I should have said it's going to be on the bottom really, isn't it? You can have shock waves anywhere you want on the tailor on. Yeah, so we'll just say we've got a big shock wave at the front there. The rest of the tailor one still works. Okay, simple as that. Big shock wave there. Yeah, the rest of the tailor one still works. So just to tidy that up a little bit. Hopefully you can still see that there. We'll stick with the word stabilator. So if you put an all flying tail or an all flying stabilator on there, right, where initially the shock wave sorry, I might be standing in the way of that. Initially the shock wave may cover the control surfaces. Now we can have quite a big shock wave on there, so that is not helping, you're losing control, but all of this area here, right, is still working. So that's still going to point down, that's still going to point up, this area is still working. So that helps you to retain control effectiveness during the transonic phase. And the best way to do that is via an all flying tail. If you look for an example of that, the F104 Starfighter, yeah, the F104, I think it's a Lockheed F104. Please get out of the habit of saying the Lockheed or the Airbus, or, you know, like people, there's a few people do that, they just mention the first name. Oh, what's that? It's a Lockheed. Lockheed's the name of a company, not the name of an aeroplane. Okay, the full name is the Lockheed F104 Starfighter. This one here is the Hawker Hunter, that's the Supermarine Spitfire. Okay, so the Lockheed F104 Starfighter, that had a T-tail, okay, so it had tail, and the tail was at the very top of the vertical stabilizer, so it put an all-flying stabilator at the top of the tail there, okay, and it had the jet exhaust at the back, right, so it was out the way of the separated flow, and it had the an all-flying tail. For P14, all-flying tail, yeah, all one piece tail surface, that's the answer to solving that problem. Okay, there's another answer where you can use vortex generators, and the vortex generators, that's on the PowerPoint. What they do is, in front, you can use them for the wings, for example. If that's you couldn't have an all flying wing, so if you want to get rid of that separated flow there, what you do is you put little vortex generators just in front of the control surface there, and instead of that becoming turbulent, okay, you make that into a vortex. Now a vortex is not turbulent flow, it is still controlled flow. So it's like not as good as laminar, but it's better than turbulent. Okay, so if you create a vortex on purpose using little blades that stick up in front of the control surface, you can make the airflow at transonic speeds where it starts to separate. Okay, or for example a shock wave, you couldn't get a shock wave over there because it would chop the shock wave into little bits. Right, so it dissipates shock waves and it stops turbulent flow. So you can add vortex generators in front of the control surface. That's another way to alleviate the problem, to get rid of the problem. Right, thanks for watching. I'll speak to you later. I had to use the camera with the bad sound again because I had a lot of drawing to do. When I've got a lot of drawing to do, I use the bad sound camera. There you go. Right, if I've got other stuff to do, I'll use the other one. Thanks for watching. That's the last pass point for theory of flight. So if you've just got the pass points to do, that's you finished theory of flight once you've mentioned that. Okay. Right. Any questions? Don't be afraid to email me and ask me. Okay. And there's also Zoom sessions going on this week as well. Check Moodle for when the Zoom's on. Thanks for watching. Bye bye.